Hey, good afternoon, everybody. Welcome to today's seminar. It's a pleasure to have Adrian Ortega here with us. He's here in Guadalajara for 1 year now. So he will be here for 1 year due to this Programa de Repatriación. And well, I know Adrian for many years. I think 2008 or so. He was a physics student at the Universidad de Guadalajara. He then did his master and PhD at UNAM. Then came back for a postdoc here, and then went to Hungary to join a group of Thomas Kiss in Budapest. He's did things on quantum transport, many particle physics, and matrix theory, and lately quantum information, and that will be also the subject of his talk.
Thomas, I'm also very happy to be here. And as Thomas said, I'm going to talk about essentially my project in the postdoc. Just for context, I was doing physically the research in the Institute in Hungary, but my postdoc was paid by this initiative of Hungary, which was a quantum information national laboratory, which is like a huge consortium involving many universities and also companies. Okay. Yeah, in order to explore this like new quantum technologies research area. So before we start. Yeah. So I just want us to do a little announcement. So in case anyone is interested in helping us with the work. So as Thomas mentioned, I have done some things in the random matrices and other systems. And they are focusing quantum transport. Also, there are some works on PP symmetry. Also one up to Thomas. It also involves a little of quantum transport. And just to be in the same line, we also did when I was here doing the postdoc, something with quantum walks and quantum chaos, which is also a program related with quantum transport. So today is not going to be anything related to quantum transport. It's going to be related with the quantum computation and quantum information. So let's see. So this is just to present the group. So we are working now. So in the institute, the two people whom I'm working is Thomas Kirsch, which is the head of the group, and also Kalman, which is a senior researcher in the institute. And we have now a close collaboration with the Duke University in the US. Essentially, by let's say a matter of luck, we managed for them to implement our circuit in their ion trap quantum computer. So Norbert Link is the head of the group, and Alaina Grind is involved in the management and laboratories. That's also a senior researcher, and Elijah is a student making the experiments. And here, the other type of experiments is below this. So below a sea of troubles. We also have to deal with the companies such as IBM, quantum computers in IBM, and the Amazon bracket in order to run those circuits. So the Amazon bracket has all the companies, which is the IonQ, Rigetti, or the Oxford quantum station. All the quantum computers that I'm going to talk about here are superconducting, maybe superconducting qubits, which is the IonQ, the Rigetti, and the OQC, and the ion traps, which is well, the results in Duke they are still not ready, but they are coming soon. So right now, only IonQ. I will show some experiments that we made there. So right now, the field of this quantum computation has grown a lot, I would say, because right now we have you have seen that the previous slide, you have companies really big companies like IBM or Amazon interested in these things. So the field is essentially exploded. So that right now it is needed a kind of classification of what people is doing what. So you can see several levels from the let's say, the physical implementation up to the final, let's say, the final service people interested in using quantum computers. So we are more or less in this level, as quantum information scientists. And at some point, we also deal a little bit with not really with the pulse schedule or the signal digitizer, but with like more low-level, let's say, low-level circuits that get implemented more closely to the physical system at hand. So, yeah. So right now, you have seen that you can access online several quantum computers. So, but right now, the quantum computers essentially are imperfect, are highly noisy, doesn't support this quantum error correction. And then the question is, what do you want to do with them, right? Obviously, you don't expect right now to solve like very complicated problems as in the normal computers. It's more like still an exploratory stage, but in this exploratory stage, you also have things that you want to decide. For instance, which technology is more promising, because it will depend on which technology you want to put your money. For instance, are the ion traps good, or the superconductings are the better ones? Or is it that you have to support all technologies, or even, I don't know, for instance, photonic chips or all that stuff, neutral atoms, in order to address several problems that different technologies are, let's say, more suitable to solve. And also, which type of tasks are worth investigating? Since we cannot solve, let's say, big problems right now, which are the ones that we can put in them? And then we can, let's say, assess the quantum capabilities regarding the noise, regarding all these problems with the technology. So the issue here is that I'm going to discuss how to, let's say, loosely we're speaking, benchmark a quantum computer, where benchmark can also mean that testing. And we are going to see that this type of early benchmark can help to decide which quantum computer is better, or if it's better, in which parameters it's better than others. Yeah. So, but then how do you do it? How do you test or benchmark different quantum computers? And then this is second is like one of the more important issues in the field, is that is a single number enough? So usually benchmark in quantum computation is understood as only one number that gives you like the overall power of the computer. And right now the first one of the first people that pushed this idea was the people from IBM. But as we have like working with them, we're seeing that so it's not healthy to try to define like just one number in order to rate different devices. And also, if we have if one number is not enough, then also which numbers do we need, and what are the characteristics of such good benchmark? In this case of a single number, this is like also a general criticism that exists in the classical benchmarking with classical computers. That in general is not enough. There's just one number in order to characterize a whole device. And also, regarding the characteristics, maybe we can use what we already know from the classical benchmarking and try to adapt their techniques to our current problems that uses the quantum computation. So, in the first part, the how to. So essentially, you have a quantum computer and you want to test it somehow. In order to test it, you have to feed them some circuits, which in general, not in general, but the idea behind is that there are some programs in which you want to test the devices. And there are essentially two areas right now. One is the area of randomized benchmarking, which is the one that pursues a lot IBM, which involves benchmark as a quantum volume, or in circuits, also like some variations of random circuits, which are called mirror circuits. The other side is to try to test significant tasks in the quantum computer. For example, some simple protocols that exist in quantum information or quantum computation. And there are even early examples right now of how to test quantum computers in some programs from quantum chemistry. So what I'm going to talk about falls most in this part here. We are not so interested in the randomized benchmarking. First, because we know some things already in it, but also for us it's more interesting to analyze if a quantum computer does what it is supposed to do. So, yeah. So the source of a good benchmark, talking about classical benchmarking, when you start to dig in if there is literature about it, or we are kind of surprised that yes, there is also a field of classical benchmarking. And here there are like some examples of classical, let's say, works in the field. And also here I also included the criticism of characterizing a computer performance with a single number in classical computation. Essentially, the paper says that it's not healthy to do it. So from here, I'm going to take the ideas of what are the characteristics of a good benchmark, and then yes.
How do we characterize by a single number? That's why.
So the problem is that usually benchmark in quantum computation is equated with a score. But the benchmark instead is more like a tool, along with a procedure and some metrics that tells you how to evaluate either the performance, energy consumption, or probably security issues in your computer. And of course, okay, so the good benchmark is the one that the problem that you have at hand, right? So you are not interested, for instance, in that I give you like a suite of testing the circuits, because at the end, what you want to do in practice is to solve your problem in the own application program. And also you have to be very careful here, because benchmarks are divided between what are the benchmarks coming from the companies and the benchmark coming from academia. And usually the benchmarks that come from vendors have certain interest in the product to be sold, as we have seen, like for instance, in the quantum volume, right? Quantum volume. So it's a number that uses IBM to score the devices. So here are a list of characteristics. This list of characteristics is not unique. Essentially, depending on what you are going to test is the type of characteristics that you ask. So here, these are just some characteristics that a performance benchmark has to fulfill. Here, notice that I am excluding characteristics for, let's say, a benchmark for security or energy consumption. So first, the first characteristic is that the workload has to be representative of real-world applications. So this essentially, the workload is essentially the circuits that you fed into the system. And this is because this is related with what I was discussing in separation between the circuits that are tested in the quantum computer. So we want, in our case, to fit a circuit that actually accomplishes a task in the quantum computer. It has to exercise all critical services provided by the platforms. Of course, I mean, you don't want to test only one part and say, yeah, this part is good, but then I generalize the good part and say that the whole device is nice. Also, the benchmark has got to be tuned or optimized for a specific product. And for instance, here you can check the one notice that came in Honeywell in 2021, where what they did was actually to claim that they achieved the biggest quantum volume in their quantum computer. But then it's like, okay, yeah, you can reach the biggest quantum volume, but is this good for general computational purposes? So it's most surely not the case. Of course, you have to generate reproducible results and not have any inherent scalability limitations. So this means that if so the problem with quantum computation is that your Hilbert space grows exponentially. So for instance, when there will be a point when if you try to benchmark the quantum computer using the quantum volume, you are not going to be able to do it, because essentially what you have to do is to do the classical simulation of all the probabilities for every vector in the Hilbert space. So as this grows to the end, it's impossible to do it. So at some point, this task is going to fail. So you need another type of circuit, let's say, that no matter the number of qubits that you have, you can still, let's say, check classically if your quantum computer is working correctly. In our case, we can do this because inherently the circuit or the task that we do can be checked classically in the quantum computer in no time, essentially, because it's just the evaluation of a polynomial. So, yes.
Can you please give the definition of quantum volume?
So it's not so simple. So the quantum volume is just a power of 2, and the exponent of the 2 means how many qubits are successfully implemented a certain specific task. So what they do is like to fed a random unitary, and then you have to investigate what are all the outputs, all the probabilities of obtaining all the states in the basis. And from there, you have to sample like the outputs that have the biggest probability. And then you have to compare this with the same circuit, but fed now in the quantum computer. And if your results, if your probabilities are more or less matched in a way, they pass a certain threshold, then you say that, okay, the quantity of qubits pass the test. If d plus 1 didn't pass the test, then you stay at d. You say that your quantum volume is 2 to the d.
But d is the number of qubits which involved for that task, which is assigned for that task.
Yes. Mm-hmm. So, like more focus on our circuit that we want to test. It's something called the quantum state matching using a super attractive map. So it's a little complicated, but in fact it's like very easy to understand. Just after like a very technical name. So for instance, so this is an entirety protocol. So it means that in each step, you do a predefined set of things that you have to do. In this case, the step is only to apply a 2-qubit entangling unitary to 2 qubits that are prepared in a similar state. Yeah, so you prepare the 2 qubits in the same state, entangle them, then measure if, for instance, the second qubit is in the state 0, and then if it is, then you accept the result, and then you obtain a final the state transform of the first qubit in this way here, where this function of a z is just a quadratic rational function this way here. So this is like let's say the most general nonlinear transformation that you can do. Why is interesting? Because if you remember from quantum mechanics, you are not allowed to do this type of transformations because these are essentially nonlinear. So essentially, what you have, the trick that does the nonlinearity to work is to do this step here, which is the post-selection. So if you do the post-selection, then you can achieve nonlinear transformations even in a quantum mechanical system. And then what you do is to apply this procedure a number of times. So in this case, you have 2 to the n qubits. And the first step, you entangle pairs of them, measure the second qubit in each couple, and then if the result is accepted, you go to the second round. Still, you play this until at the end, what you end up is the composition of your original function n times. Yeah. So in our case, let's say the nonlinear transformation that we want to implement is very simple. It's just this z squared over epsilon, where epsilon is a positive small number in general. So the idea is essentially that this set describes the state of the system. So for instance, in this set, I write it like this. And this is going to be the position in the complex plane. But then using a stereographic projection, I can also understand the state in on the surface of the Bloch sphere. So the state either lives in the plane or in the Bloch sphere, and then after each state, at each step, what it's going to do is going to square the initial positions in this way and scale it by a real factor. In order to apply this transformation, the entangling unitary, one entangling unitary that can be used is this one here. which is this epsilon. It's not unique, but in this case, this is the one that we use. And so in order to implement this unitary into any quantum computer, we have to translate it into gates that the quantum computer can understand. So in this case, there exist the compositions which you can work out how these will look in terms of 1 qubit gates and CNOTs. So this is like a technical detail, but for this specific entangled unitary, you only need 2 CNOTs in order to achieve this part, which is a good thing because in general, any 2-qubit entangled unitary will use 3 qubits. Will use 3 CNOTs. And then the issue with the CNOTs is that physically, what you do in the quantum computer is that you somehow interact with 2 qubits, and these are the most biggest amount of resources that we have in the quantum when executing the quantum circuit. So you want to always to minimize the number of CNOTs. And regarding the task, or about why this is called this state matching, is because if you imagine that you have a state and you have a reference state, and then you have the result, a state that is the result of a computation, and you want to see how close this state is to the one that you expect. So this is a very natural thing, because this state that is not the one that you are looking for, you can still accept it if it's like, let's say, in a kind of error domain. So this epsilon here, what it quantifies is the error threshold in which you are going to accept as valid your answers, the answers that are around the reference state. So what the dynamics of this map is that if you start, for instance, in this position here, which is an angle that is less than the radius epsilon here, then each time you iterate, you are going to approximate the reference state. Yeah. So it's like a kind of orthogonalizing procedure, because if you start, for instance, here, which is outside the prescribed neighborhood, if you iterate this map, you are going to end up in 1. Yeah. So what you do is like, okay, you have one state that you don't know what it is, but then you apply this map, and if you end up here, you say, like, look, I got a good state after my computation. Yes.
So for example, in this mapping to this stereograph mapping, do you ever have trouble because the poles are basically the infinites? So this, I think this is in the polynomial that's set as per. So this needs to be valued infinite to get poles in 0 and 1 states, right? Is this a problem there?
Not really, because in the circuit you work in the box field, and here everything is compact. So here you can include here you have to include the infinity, but if you work in the surface, after a few steps you end up close to 1. So you only have the angle of theta close to pi. This is the so it depends on how do you want to see it. One of the characteristics of this map, like mathematically oriented, is that it is super attractive, which means that it has fast convergence. So with a few number of iterations, you can reach the result that you want. Let's say for analyzing some quantum state. And also in n steps, you are going to need 2 to the n qubits. This at first, it might look like a hindrance, but when you want to test like very big quantum systems, it's actually an advantage, because let's say that at one point you test all your qubits in your quantum computer. Don't worry about that. And it scales very quickly, right? So it has like a long lifetime of these secrets of say. So it can be applied to very, very big devices. And as I said before, there is no classical overhead, which means that the result that you expect, you can compute it in a classical computer. So essentially, the result of the figure of merit that we look for is this success probability, which is computed in this way here, where this theta is the initial angle. So if you want to compute the success probability after n steps, you use this formula. You can compute it in the classical device, and then obtain a number, and then check what was the results in a given quantum computer. So the idea with this is that this is like a kind of discrimination between if a quantum computer is good or bad, like in a very coarse manner. Because if you think about if you think for a moment, the experimental success probability is something like this, which is expected value, plus minus some statistical deviation, which is quantified by this standard deviation, which is the usual standard deviation for the binomial distribution. And what do you expect is that if the number of the space goes big, then this number is going to be small. Yeah. So this is the let's say the first set of results. Let's see. So this is the results for one step of the protocol in two quantum computers. Both were from the IBM. One was Manila and the other was Lima. And the reason why we chose these two was because the Manila in the IBM score has a quantum score of 22, and Lima has a quantum score of 8. So here in the first line, we see in the first row we see the experiments when the initial conditions over 5 are taken in an ordered manner. Yeah. So in order to compute each of these points, we fixed a value of θ0 and then selected an equally spaced quantity of π0 values, which are the initial positions of your qubits. And then see what came from the experiment, and then you have these results. And then here you can see, for instance, that Lima is a little bit worse than Manila. Yeah, because at this Manila, it's always like in the threshold, in the statistical threshold. So here you can say that, okay, look, Manila performs well and as expected because it has a bigger quantum volume. But for instance, if you change a little the parameter of which is this epsilon, which is the radius of convergence, then the results start to approximate between each other. So what this figure tells us is that it depends a lot what are the inputs of your parameters in your circuit. And also, if in this row here what we did was to change the values of the initial phi zeros instead of being like an ordered sequence, which is randomly between 0 and 2 pi. And then what you see in the results is that all results are more or less coincident. So what you see is that you average out the errors. So it doesn't matter that if your quantum volume is bigger in one or the other. If you select like a good initial conditions, say, you can obtain a similar performance here or it's epsilon, but see what that. This is another test, but with more quantum computers.
Sorry.
Yeah.
So this basically reminds me a lot of, for example, when you compare strong quickly to environments, you don't end up with something like each stage or something like that. So you end up with something different. Do you think this is related to that? Because this depends on the initial conditions, basically.
So in this case, it's more like so from all the possible sets of results that you can have, you can have like, let's say, good results that the machine can operate, good parameters. But then you also have bad parameters, yes, badness of control. And what you do in the random is like to select from all this, and then you wash out the.
There's also a detail that technically, I mean, this quantity, we do only one step. One step, we need yes, they could do this one step in parallel. So the machine has 8 qubits. This step right for the first 2 qubits, for the second 2 qubits. We try that.
No, we didn't try this, but I don't know if you have problems in the with the second step. If you have like more than one step, but it was only for 2 qubits. So in the previous plot, we, let's say, average out the value of phi 0. In this case, we investigate what happens when we change the phi 0. So for this case, we fix the initial condition of equals equal to pi over 8. If you remember, the success probability does not depend on phi 0. So if the quantum computer is very good, then this success probability is constant. Yes? And this is depicted in this line here. So this is the expected one with their threshold of statistical error, and then you have different results for different quantum computers. Here we also include the devices from Amazon, which is a Lucy and IRQ. Okay, first here you can see aside that you can distinguish which are statistical errors from which are device errors. For instance, here you can see that these two quantum computers have the same quantum volume reported, but one is always better than another one. So it seems that the task of optimizing, let's say, the device for a certain for the quantum volume score somehow misses some important things when you want actually the quantum computer to do something. Also, something that is noted here, for instance, in this trend here, or in this trend here, which looks like an inverted sinus, it seems that there is not only statistical noise, but there are superimposed some behavior here. Here is very clear that there is some behavior here. And then immediately, if you see this signal here, you think that you can be able to describe why this happens. So is it like a decoherence process? Is it like a coherent error? So how do we take it into account? So this is the, yeah. We also did 2 steps, and here, as expected, the results from the devices are worse, simply because you have to apply more gates in the experiment, and then to have accumulated errors, more interference, etc. So here you have like none of them like matches or falls in the expected threshold, and yeah, and also not even the IRQ, which is usually the best quantum computer available in terms of accuracy. So from this, okay, what to do with these results? How to draw some score for them? So since at this level we are using like a kind of a statistical discrimination, so one thing that we can do is to compute certain kind of distance between the expected distance and the experimental one. And in this case, we just plotted something that is called the total variation distance, average over the different values of initial condition phi 0. And then here, what we have is like a first score on how the quantum computers implement 1 and 2 steps. Yes? So you can see here in this line above all the technologies that are superconducting, and here below the ones that are from trapped ions. And you can see that okay, this trend does not necessarily follow the values of the quantum volume. Sometimes, for instance, in this case, the Lima is a very good quantum computer for this circuit, even though it has a low quantum volume. And also, more interestingly, you can see here trapped ions that are more or less in the same performance as these 2 superconducting qubits here and here. And this is interesting because so there's always like this competition between technologies. And for instance, in the trapped ions, I think a year or 2 years ago, there was like a paper that says that the trapped ion has the lowest fidelity in their gates, lowest compared to the superconducting qubits. Later, I think this changed because the IBM people could manage to improve their single qubit gates. But at that time, it was like a distinction that, look, superconducting should be better because individual gates are usually better. But then if you fit a circuit and you measure the performance, it can be competitive with still the superconducting technology with the trapped ions.
So I think you mean placing a network of qubits or
By what?
by bit? Oh, by fitting, you mean like putting several qubits?
Very massive. Take with an experiment with the ions and solid. Okay, on more or less the same.
With this circuit.
This is several qubits circuit, right?
It's in this case it's only 2 and 4 qubits. Mhm. So even we cannot do, let's say, 3 steps, because 3 steps you have to use 8 qubits. And we did for 3 steps in IonQ, but we have problems with the device. For some reason, the circuit was not executed properly. So this is why I don't show 3 steps.
So I come, sorry, I just came late and I have a lot of questions.
Yeah, no problem.
Also, for example, there should be a lot of things happening there, right? So it's not only the fidelity about the single qubit, but also, for example, the interaction between these qubits, or the readouts also happening there. Is this something happening? I mean, are you able to distinguish these errors are coming from which parts, or intrinsically because of the way of the qubits are built, like light, optical, or superconducting, or
So there are things known because of the people that build the devices, know more or less the technology. So for instance, for a superconducting qubit, it is known that a big amount of error comes from the measurements. That by the way they have to measure, they can use a lot of measurement. And this is why people from IBM pushes a lot this type of mitigation error techniques, because it's a way to correct this type of measurement errors. The biggest source of errors in the IonQ, one of the biggest source, I think, is the interaction. Because by the way you build the trap, all qubits are coupled to all other qubits. So it can happen that that if you want to excite these 2 in the corners, all of the others get excited. It's also like a good thing for the MRAPs is that once you have the setup, it can last probably, if I remember correctly, like 1 or 2 hours. You can run experiments for 1 or 2 hours, which is a lot compared to the superconducting. And so the problem with these things is that you have like a hint of what is happening there. But if you want to put everything in a theoretical model, the theoretical model soon starts to become hard.
yeah.
So here we try to characterize it like the other way around. So we have the results and we want to see what can we say about that. And this is what coming next. So and now this is the let's say the most cluttered slide. So immediately the first thing that one thinks is how to model the noise in these devices. So one natural way to do it is using this channel approach, quantum information theory. And then when one starts to read the papers, one notices that they always, or they most of the time, try to simulate the noise theoretically using the depolarizing channel, because they say that in quantum information protocols is like the most dominant channel, the most dominant type of error that you can find. But now it happens that this depolarizing channel is not, let's say, particular to the quantum information protocols. This depolarizing channel has also been applied to other circuits that are not quantum error correction, but they also did some experiments with this model here, the polarization. And it happens, the reason why you can do that, it's actually like for me, a very nice mathematical statement that, so essentially, if your channel, any channel that you want, say lambda, computes with every member of the group of unitary matrices, then it's a theorem you can prove that on average, this channel is going to be the depolarizing channel. So it's quite surprising for me and quite useful, because Now you can say, like in the like from point of view random matrices, okay, we want to characterize the channel like in an average way. And then what you can do is like to average some channel, whatever you like, over the whole unitary group. And then what you will end up is that is going to be applied as a depolarized effect. And then, okay, so we have this information, and then we feed it into our protocol. And so this is essentially the results of applying the depolarizing channel into a protocol after n steps. So this row n here is essentially the density matrix without the depolarizing, the pure state, let's say. And and here we are assuming that, let's say that you apply one iteration of your protocol, and then the depolarizing channel acts in the whole quantum computer, all the qubits. And then this is characterized by some probability pi over j. And then if you apply iteratively this map, you can end up with an expression like this. But this p tilde, it contains information of all the probabilities that in principle can be a little bit different between one step and the other. And now because you have this, then you can compute from here the success probability, and then you end up with an expression like this. And then this tells you that the success probability here still does not depend on the phi 0 angle on the initial phase. So this means that at most, the application of this channel is going to move your results below you have the success probability here, it's going to move them below the one maximally based. And then you ask the question of how do they come the oscillations that we saw in the data. So this is good because we have, like for instance, with this, it might be that we can reproduce, we're in the process of doing this, but we can reproduce this trend here. See? This can give you the depolarizing channel can give you this linear decay, but not this type of inverted oscillation. Now the next step is to try to address some more difficult stuff, which is, for instance, how the gates are implemented in the circuit. So one source of errors that are commonly reported for the devices is the effect of the NISC rotations, which can be over or under rotations. And now, as you remember, because of the CNOTs, couple more than one qubit, they contain the more amount of error. And then in order to implement a CNOT, you cannot implement a CNOT, say, hardwired with pulses. What you have to do is somehow do a unitary transformation to the two qubits in this way here. And then if you select this rotation with 1/2, essentially you have the C. You need another one qubit case, but this is the qubit that entangles the two qubits. And then you can introduce here parameter alpha, which accounts for the NISC rotations. Now, if you do this, then you have a model that includes the polarization and over or under rotations. And then here, this is an example of a signal that we obtained in one of the experiments. And the red line is a theoretical model. So at least in this approximation, it works very well. This is a little bit of cheating because here I did, instead of implementing the whole circuit, I implemented the case where epsilon is equal to 1. And in that case, there is only one CNOT. I mean, the whole matrix can be replaced by one CNOT gate. And then it's easy to work out the algebra. And then this essentially is a function that you can obtain analytically. In this case, which is these points here are repeated from the previous plot. In this case, it's more complicated because in order to obtain this curve here, we have to add errors in the one qubit gates and in the two qubit gates. And then by doing like something like radical fitting, you can obtain this line. It's also describes very well. So right now, what we believe is that these two things can be enough for describing the results. And we are doing this part more thoroughly. Yes.
So Just in the previous slide. So, what's the narrow model? So, does this alpha is this a random number then, or what is the error number?
No, actually, in these cases, what I did was to keep numerical. So you have a function.
This alpha depends on phi.
Yes.
Yeah.
So you can with these gates, you can do the for one step you do the algebra and you compute the success probability, which is a function, and it's not going to be not also a function of theta, but also on phi. And then you this phi is going to this alpha, and then you fit numerically with the experimental data.
And assume in some sense that if you do 1,024 shots, then at each shot is multiplication.
Yes, because here we have, let's say, experiments. It's an average of the experiments. No, it's more than that. It's like 5 times 1,000. So we try like to put here's the average, and then over this average. Because in other case, yes, you can have this point somewhere. Yeah, and yeah, so yeah, some quick outlook. So first of all, didn't mention didn't stress it too much, but our circuit is a highly structured circuit because we have the decomposition, and this decomposition is applied one and again in the same quantum device. So this means that the amount of transpilation, which is kind of a compilation between what you give to the quantum computer and the gates that are going to apply physically, is fast. As we saw, there is no classical overhead. We can compute theoretically all the results in a classical computer. We have a big testing advantage, and at some points we would like to do very big quantum computers. So the success probability that I show depends only on like some very particular output states in the whole Hilbert space. We can also pose the question: what happens if I want to test different combinations? So you can do this, but then you have to include swap gates in your circuits. And essentially, right now, swap gates are not good. It's not good that you have swap gates in the circuits because they are constructed, I think, like 3 synods, and then this puts a lot of noise to your results. So we only like test like very well-ordered pairs of initial states. Yes, in the experiments, we can observe also time variations in the scanning of the initial conditions. We saw in some of the plots that it seems that if you select the initial conditions to be random, then the results are better, which is something that you don't want to do. You don't want to average out errors. Also, the equal quantum volume does not imply equal application of nonlinear transformation, and this is always like also already said with other types of circuits that the gate is always like a lot of noise, and the most or one of the best devices is the IQ, and the IBM devices are some. And yeah, that's all.
Or anybody has any question? I do. This is about this depolarizing way of. So I think if I remember correctly, you need to know more or less the stationary state that you will end up doing. Not necessarily.
No, it's only that the row is pure.
So it means you put row in the state that you are projecting to.
Or you assume that the row is pure.
Okay, so somehow, if, for example, I'm thinking about thermalization of our processes, and but this is not happening. You assume that this is not going to happen.
No, because if you assume that there is noise in the protocol, then this transformation it's more complicated because now your qubit can go inside the block sphere, but still you can compute the fixed points of the map. But I don't remember correctly how they are distributed. But it's more complicated.
The fact that you assume that there are no error, there is no noise, right? When you try to model an error, the imperfection of the protocol, assume that there is no noise.
So in this depolarizing, there's no noise, but then if you include the over rotations or under rotations, this can be taken as noise.
But what if they are always the same in fixed alpha, right? So
They can be the
for
same.
this 5,000 shots, it's always we assume that it's always the same unitary.
So it's the same unitary, but the this can be some value, some small value around the 1/2. So yes, not in this case because it's the flipping polynomial, but each time you do the experiment that you couple the qubits with the CNOT, the alpha is no value.
This is not taken into account.
Here I didn't take into account because I work with the average.
Okay.
But then another option
would correspond to the fluctuation.
Yes, for instance.
What else? No, there's not. Good, I am.